So Guobao Wang is a professor of radiology from UC Davis, very well known to many of us for the kernel EM method, which is an incredibly powerful methodology many of us have picked up on, where he published that in 2015 with Jinyi Qi. And today he'll be presenting on that topic. And maybe just to mention as well, recently recipient of the IEEE Medical Imaging Technical Achievement Award 2025, so a very fantastic track record in image reconstruction and in kinetic modeling. So with that level of introduction, over to you, Guobao. Many thanks.
Thank you, Andrew, for the introduction, and thank you so much for having me here. It's a really great pleasure. Today, I will talk about kernel methods for image reconstruction. So this is a work that has spanned over more than 10 years, but I promise my talk will be much shorter. Okay. So it's very interesting that ideas in machine learning comes in cycles. So basically, neural networks was very popular in the 1980s. And then kernel methods became dominating in the machine learning field in the 1990s until early 2000s. Okay, then of course, nowadays, all deep neural networks stayed on the central stage. So a very natural question for us is, where do kernel methods may fit today? And in my talk here, so I will show you how kernel methods may provide a unique way to bridge physical space reconstruction and learning-based approaches. Okay. So image reconstruction is fundamentally a physical space involves problems. The physics provide a forward model to link the unknown image X to measurement data Y. So for PET, of course, the data follows a Poisson distribution with the expected projection model Y bar equals to this system matrix P times the image X plus the mean background events. The classical inverse problem then estimate the image using the maximum likelihood as shown here, and then very elegant algorithm is EM algorithm that we have been using all the time, even for clinical scans. So another way to think about image reconstruction here is from a geometrical perspective of image work source. So for this standard maximum likelihood reconstruction, actually work sources are treated independently, as shown by the graphical illustration here. So the image space is actually just simply the Euclidean grid, okay? And then work sources are only covered only through the imaging physics. As part of this result, then normally we see the ML, the maximum likelihood estimates is very noisy, especially under the lower count situation. And usually we can add a regularization to stabilize the estimation, which introduces the work source coupling. So through adding a penetrative function, Rx here. And of course, beta is the regularization parameter. So this leads to the well-known penalized likelihood or map reconstruction. And typically, so this regularization is quite local and handcrafted. Okay, so this has been well studied since the 1990s. So we study how to turn the beta parameter, how to design the regularization function Rx here. And of course, in recent years, deep learning image prior have been increased in use for this purpose. But at least one remaining charge is still on the optimization side. That's also experienced Chris is still running a optimization challenge along with this symposium. Okay, so the kernel methods takes a different perspective. So Jingyi and I started this research almost like around 2012 or 2013. So we represent an image using a kernel representation. So here is equal to just a kernel matrix K times the kernel coefficient image alpha. So this kernel matrix K is not arbitrary, but specially designed to be a squared and positive semi-definite. So with this kernel model, then we can insert the model into the folder projection model. That gives us a new expected projection model equal to P times K times alpha. So with this linearized model, so the image prior information is incorporated directly into the folder projection model instead of being put into the regularization. So in this way, so we can still use a maximum likelihood approach to reconstruct. In this case, is the kernel coefficient image alpha. So how exactly we can build this kernel matrix? So this requires to use the kernel trick, which is quite famous back to the year of those kernel methods in machine learning. But for image reconstruction here, so we treat each voxel as a data sample if you use a machine learning language here. And each data sample, of course, is associated with a feature vector f. So the assumption here is that the voxel intensity is then viewed as linear in the transferred space of f. So as you can see from this equation, okay. Equivalently, so this expression is also just equal to the linear kernel expression here shown here. So because that transformation only appears as a inner product in the expression. So then in that way, we only need to define the kernel function instead of computing the transformation, which is much harder to do. So this here is the kernel function, then compute the similarity between voxels. So what makes it powerful in terms of producing practical use is the kernel defines voxel relational geometry. So because in this case, instead of reconstructing the voxel intensity directly, so we estimate the kernel coefficient image. And instead of just the voxels are no longer just Euclidean grid, but instead of lying in this non-Euclidean embedding space defined from image priors. So on the left, so we are showing a regular like 3D image from a cardiac FDG scan. So you see the images are displayed on the regular Euclidean grid. But on the right side, we are showing this 2D visualization of the voxel embedding using UMAP. So with this embedding 1 and embedding 2, so we can see, so all the voxels are now follow a structured pattern there. So you can see, can we see it? So basically, so for example, so the myocardium voxels stay in this cluster, and then the lung stays in this cluster. So with this structured pattern in that embedding space, so then the reconstruction occurs on that restricted intrinsic structure. So this may lead to improved image reconstruction performance. And over the years, we have developed several applications. So I'm showing the 3 applications. So the first one is, of course, dynamic path. So in this case, we use composite image from longer frame to serve as an image prior. And then we use the temporal features extracted from the longer frames as a feature vector. So then using those feature vectors, we can build the kernel matrix. Okay. And then the kernel method is used to reconstruct those shorter frames. On the right, we are showing like just 2 examples, one for 10-second frame reconstruction, one for reconstruction of a 1 minute frame. And the kernel method provides much significant improvement as compared to the standard wind reconstruction. So this method is now available in UIH research package for the investigation. So, and also in the field, there are multiple groups with effort in this space for MR-guided pattern reconstruction. So in this context we can use MR as an image prior to guide the pattern reconstruction. So the feature vector is mainly a local MR patch. And then we use this MR image prior information to guide the pattern activity. So the image shows one example generated from Andre's group, showing basically, so along with the decreased count levels, so the standard ML-EML reconstruction is getting noisier and noisier. On the other hand, so the kernelized EML reconstruction stay quite stable across different count levels. We also applied the kernel methods to PET-enabled dual-energy CT imaging. So in this case, in the context of PET-CT, so we can use the X-ray CT as an image prior, and again we use the local patch as a feature vector. So then we use this kernel representation to reconstruct the 511 kV gamma ray attenuation map from the PET emission data. So for those who work in PET area, so this is known as MRA reconstruction. But the standard MRA would only provide a very noisy reconstruction of the 511 keV map. But with kernel MRA, now you can, because we use the X-ray CT as an image prior, so then we can get a much improved image quality. And then we can combine this 511 keV attenuation map with the standard low energy X-ray CT to form a dual energy pair for material decomposition. Okay. So with this, so far, the feature vectors were manually designed. For example, either from temporal features or MR patches for different applications. One natural question in the era of deep learning time is, can we learn the voxel representations? For example, once we have the voxel data from image prior Z, and then can we build a neural network to extract the embedding, and then use that to build the voxel similarity kappa here. So that's about our deep kernel representation work. So in this work, so we then unfold the kernel construction process and replace it with neural network description. So in that way, we make kernel construction to be trainable, which is represented by this model here. So you can conceive this x equal to k parameter with theta times alpha as a special type of neural network. But it's specially designed for its form here. So basically, it still forms a linearized form between k and alpha. So the beauty of this formula is once theta, the model parameters, is determined, then the model remains linear with respect to alpha. And alpha will be reconstructed from the projection data. So in this way, the reconstruction remains a linear like the inverse problem, but we still benefit from this nonlinear deep learning. Okay. So this slide shows you a comparison between the handcrafted feature, which is our standard kernel methods, and the deep kernel learning derived embedding visualization. So you can, if you compare these two, so you can see after this deep kernel learning, so the structure appears more structured. And you see, so for example, so the aorta is now more focused on this area instead of scattered. And so in this way, we hope, so this learned voxel relational geometry can improve image reconstruction. So this is demonstrated for reconstructing a 2-second frame in dynamic cardiac FDG PET imaging. So basically, so if you compare the deep kernel reconstruction with the conventional kernel reconstruction, so you can see a significant image quality improvement. And compared to other potential approach that you can directly insert a nonlinear neural network into the reconstruction, you can see so the image quality is also improved, just because it is more stabilized structure through that linearized model. Okay, so our kernel methods have been highly rely on single subject image prior. So this is actually a very nice feature to have, because then you can apply all the deep learning to that single subject without requiring external data set. Sometimes may cause like stability issues. But on the other hand, so this approach, this single subject approach actually still have some challenges. So number one is, what if your image prior is not of high quality, but instead low quality? For example, at low count cases, the image prior does not have a high quality. On the other hand, so the kernel learning also requires actual computation. So to address this problem, so we started to explore the pre-trained deep kernel construction by using high and low quality image pairs from population data. So in this way, we can use population learning to benefit the deep kernel construction. So this is especially relevant for the PET field, because in recent years, so we have observed that advent of ultra high sensitivity total body PET scanners. So with total body PET scanners, we can actually generate a pair of high quality and low quality training data set to serve deep learning purpose. So in this case, we still follow that kernel representation, but utilize a training data set. So here I want to make two important clarification. Number one is this network here learns to how to construct voxel geometry, but not the geometry itself of a particular patient. That means it's more generalizable. Second is the voxel geometry remains subject specific just because of this model. So here, so the K matrix, which depends on the input image, the low quality input of the image prior. So this slide shows a comparison between the single subject deep kernel derived UMAP visualization and also the pre-trained approach. So they are from the same data set, but as you can see, so all different components according to different organs, now they are even more structured within this embedding space. That also would we would improvement for image quality when we apply the pre-trained deep kernel methods for different applications. So the first application is again still for dynamic imaging, but this time the benefit is expected to transfer to those short axial field of view scanners if we train the deep kernel construction using the high quality total body PET data set. So this just shows one example for parametric imaging purpose. We are showing here, so the FDG delivery rate K1 from dynamic images. That's what, for which the data was acquired on a GE-DST scanner. But we are showing the conventional kernel result, the deep single subject deep kernel result, and the pre-trained deep kernel result. So the pre-trained deep kernel result was derived from total body PET data set. And of course, in this case, so the G scan data set was not seen by the training process. So you can see there's a significant improvement even compared to the single kernel approach here. So this pre-trained deep kernel construction also has potential for static pattern imaging, because so far the application of kernel methods is mainly for those situations where you can find high quality image prior. But for static pattern imaging, especially under low count cases, you do not even have like high quality image prior. What you can have is perhaps a OSEM reconstruction, which suffer from some low quality image quality. But with pre-trained kernel construction, that situation may change, and that triggers the application of kernel methods for static pattern imaging. So in this case, again, so the kernel construction was trained using FDG dataset from total body PET explorer dataset. And in this case, we apply the pre-trained kernel methods to a different radio tracers data PET. On the left, it shows the reference image from a regular clinical scan, and then we downsample the count level to a factor with a factor of 20. Then you can see, so the EM reconstructions appears very noisy, and also you may apply those state-of-art image denoiser to the noise image. That's what you can see from the 3D DDPM reconstruction. That's actually from Kwang Gong's group. Then we apply the pre-trained deep kernel methods to this data set. And now you can see that's, so first is much improved as compared to the OSEM reconstruction, but on the other hand, as compared to state-of-the-art denoiser, so you can see that's also improvement. In this case, is providing a much clearer visualization of the vessel wall from this deep trained kernel methods. So this is my closing thought that from the time that I was preparing this presentation for this symposium. Okay, so because so far all the deep kernel training occurred to our own group, right, which requires a lot of resources, GPU, all those stuff, especially in this year, so all the GPU computer price are increasing very fastly, right? But on the other hand, we have many groups who are working on training, like deep learning applications, for example, in this case, building all different deep denoiser for image denoising purpose. They are powerful, but they belong to image process denoising, so they have some limitation, especially according to being quantitative for quantitative PET imaging purpose. So this deep denoiser can be used alone for image denoising purpose, or they can be combined into reconstruction process, like through plug and play, or this red denoising by regularization process. But that formula would remain kind of a nonlinear, is difficult for organization. So one question would be, can we extract voxel relational geometry from this powerful deep denoising? Of course, I did not have time to test it very well, but we can do a sort of experiment by looking at the Taylor expansion, for example. So here, so if we have a deep denoiser D, of course with model parameters theta here, right? And if we do the first order Taylor expansion, so then we can get the Jacobian matrix with respect to X, not with respect to theta, in this first order approximation. So then that's a work in the field of kernel methods for general machine learning that's called neural tangent kernel. So inspired by that ideas, we can actually build a different kernel matrix here, K, which is equal to just the Jacobian matrix times its transpose. So this actually provide a kernel matrix for us to potentially look at whether how different deep denoiser may encode voxel relational geometry. If that geometry makes sense, then we can directly use that deep learning trained voxel relation geometry for kernel reconstruction. So in that way, so we can use kernel reconstruction to make a kind of bias correction for all those different deep denoiser. Okay, so with all these different perspectives that I just shared, so my summary is quite simple. So the kernel reconstruction can be simply viewed as a imaging physics multiplied by voxel relational geometry. So the physics comes from the medical system, and the voxel relation geometry can be derived using all different deep learning approaches. So in this way, the kernel framework provides a unique ways to bridge imaging physics-based reconstruction and learning-based approaches. So I would like to thank all my lab members who contributed to the kernel method development directly, especially Siqi Li, who is now the major person leading the deep kernel methods in my lab. And of course, collaborators and the senior advisors, including Simon Cherry and Jin Yiqi, who are sitting here. It's quite good to have a reunion here for our Yosedavis people. And I do want to take this moment to thank Dr. Jin Yiqi again. So the early kernel method development was carried out in his lab at the time. I was still his trainee. So I'm really grateful for all his mentorship and all the stimulating environment he created. And of course, all the funding support. And thank you for your attention.
Thank you so much, Guobao. So do we have any questions for Guobao? And please do check the Teams chat as well. If not, I'll get us started. I mean, it's a fantastic kernel method. Obviously, my team have adopted it as well. I guess for me, a lingering question I always have is that you still end up with a maximum likelihood estimator for alpha. So whatever way you find your kernel, you're still a maximum likelihood estimate for alpha. So are you ever concerned about choosing the number of iterations to do for finding the maximum likelihood estimate of alpha? And when do you stop? And maybe there's a better approach for regularizing even for alpha? What are your general thoughts on it still being a maximum likelihood problem and with all the issues of potential overfitting?
Right. So this is a really great question. Actually, so there are works from other groups which I did not mention in this talk during time. So they extended the kernel method from maximum likelihood estimation to actually penalized likelihood estimation by adding extra regularization. For example, using even the graph methods, because actually so here the voxel relation geometry can be further extended to graph methods like by using those graph Laplacian formulas. Okay, so then one challenge would be, and of course this perhaps also related to personal favorite, would be like then you require convergent solution for the penalized likelihood. Then you require many iterations to get a stable estimation. One beauty of the MLEM would be you can do early stopping. Sometimes you may consider that a disadvantage, but for my personal choice, I would consider as an advantage, because then you do need to run for many iterations, but instead just choose early iterations. And of course, that still requires some empirical selection, but it works pretty well in terms of getting stable practical performance. That's generally for pad reconstruction. Even for static, you only require like around 50 equivalent EMO iterations, 50 to 100 iterations, which is fairly simple to choose. Instead, then otherwise you need to choose the beta for penalized likelihood. Sometimes not that intuitive to do. So in this case, perhaps for my own research, I would stay with ML estimation, but certainly I think the field should be open to all different options that because eventually regularization is still one of the mainstream approach for achieving the different ways for better reconstruction.
Thanks, Guobao. Other questions?
Yes,
Dennis.
we have a question from Teams.
Okay.
So question from Dimitra. Do you think there is a useful notion of kernel induced in the identifiability loss? For example, conditions under which two biologically distinct uptake patterns become observationally indistinguishable after projecting into the kernel subspace?
Yes, I think so. One risk of the current kernel construction is sometimes, yes, you may lose some information if that information is not built from the image prior into the kernel matrix. So that's a potential risk. So then that can be potentially addressed by how you can utilize deep learning to make sure that information is included into the kernel matrix. And of course, that happens to all the different image reconstruction methods. Then it's still a way whether you can keep that useful information in your image prior, how you can use deep learning to extract and make sure that information is converted to the kernel matrix. But otherwise, it's always a balance between noise suppression and preservation of those, for example, small lesions in your prior and then subsequently in your kernel matrix. I hope that answers the question.
And there is another one from the same person. Would a graph Laplacian or reproducing kernel Hilbert space viewpoint clarify when the method is effectively imposing smoothness and when it's imposing a stronger manifold hypothesis?
I'm not sure I got it clearly. Can you repeat that?
Would a graph Laplacian or reproducing kernel Hilbert space viewpoint clarify when the method is effectively imposing smoothness or when it's imposing a stronger manifold hypothesis?
Right. So I'm not sure I got a fully understanding of the question, but I will try my best. But yes, so when you build that manifold through basically the kernel matrix is kind of encode a manifold assumption there. Again, so it may have the risk of losing some information there, but sometimes then it's still a matter how we can do a better deep kernel learning job to make sure useful information is embedded there. But otherwise, I think I can look at the question again to see if I can provide a better answer.
Thank you.
Got a question from Harry.
Yes, thank you. Since a lot of these data sets are affected by various effects that we don't necessarily model, including motion and potential mismatches,
right?
Do you think that the kernel reconstruction approach can potentially alleviate these errors or could make them more enhanced?
Yeah, that's a great question. So it can be either way. So based on from our experience, sometimes, for example, for dynamic imaging, so if you have a motion mismatch across different frames, and somehow the kernel method can actually blur all those motion mismatch and provide even better performance for parametric imaging, like for example, Petra KI. But on the other hand, we also saw some amplified effect from motion mismatch across different frames, and then somehow that's a more even severe motion artifacts in the final parametric imaging, which was reconstructed by the kernel methods. So either way, I think the most appropriate approach would be to incorporate the motion correction into the dynamic reconstruction. In that way, we may further strengthen the performance of the kernel reconstruction. So that hopefully, so if anyone works in motion correction, that would be great to collaborate and push the method forward.
Was there one last question? Yes?
Yeah,
Edo?
trying to get back into.
Well, at the same time,
right?
it'd be good to have also extra time for questions for Hung-Jing.
It was impressive to see the deep kernel method that basically show voxels as part of structures, right? How does it deal with anomalies like pathologies or something like that? So if I have something that is not expected to be there, as part of aorta or whatever other.
Right, right. So actually, so the kernel method has a tolerance of like a structure mismatch. That's you could see from the PET MR reconstruction. Sometimes a PET signal does not appear in the MR space, but once you build the kernel from the MR prior, it still be able to show up, for example, a pathological signal there. So that perhaps it can be explained by the special structure of this kernel representation. You always have that alpha, the kernel coefficient image to be further estimated from your projection data, not fully just follow the kernel matrix K. The K only provides a high level of structural guidance, but on the other hand, so the alpha image to be estimated would make some correction in terms of being quantitative. So that's my understanding of the method itself.
Okay, so thank you, Guobao, for a fantastic presentation. Let's thank the speaker again.